Go look at an example where an inventor has proposed to build a device. The idea is that it will continuously create cold and hot air from a high pressure airstream at room temperature. So basically it will separate room temperature air into hot air and cold air. And the claim is that if a feed is at 25 degrees C and 10 bar pressure coming into the device, you can obtain cold air, in the diagram here, cold air at 0 degrees and 1 bar, and hot air at 40 degrees and 1 bar. And we're feeding 25 degrees and 10 bar air into the device. There's no energy being added, no moving parts, no heat loss to the surroundings. And the question, is this possible? And if it's possible, what fraction of the feed air can actually be converted to the cold air for these two temperatures? So this is basically a second law problem to determine if something is possible. Doesn't mean we can do it, but at least determine if it's possible. We want to look at the total entropy change and determine, is that greater than 0? So in order to look at the entropy change, we need to do a first law balance to determine what fraction of the air, and let's call that X. So that's a fraction of the air that goes out as cold air, and then 1 minus X is the fraction that leaves as hot air. So you could look at this as a basis of 1 mole coming in. X moles leave cold air, 1 minus X leave as hot air. So we're going to do our first law balance to determine X, and then we're going to do a second law balance to determine, is delta S total greater than or equal to 0? If it's less than 0, we can say this process cannot take place. And the first law balance is essentially that the total enthalpy coming in is equal to the total enthalpy leaving the system. And so the easiest way to look at this is taking some reference and saying the enthalpy in 1 mole, heat capacity per mole for air, and we'll take the temperature difference relative to a reference temperature. So I reference all the enthalpy the same reference temperature, there's no reaction. So this is the acceptable way to do it. So I have X moles times the heat capacity that's cold temperature, so 0 minus T reference, and 1 minus X, heat capacity 40 minus T reference. Now I can simplify this, so clearly the heat capacity I can cancel out, and the reference temperature is arbitrary, so let me make the reference temperature 25 degrees. Left side is 0, right side is 0 minus 25. And 1 minus X, 40 minus 25. We can pick any reference temperature as long as they're consistent. We're going to get the same answer. This simple equation, we can solve for X. We get X equals 0.375. So we're saying about 38% of the air leaves as cold air, and then 62% leaves as hot air. So that's the first law. The first law then, if indeed the second law gives us the result that the total entropy change is greater than 0, then what fraction of the feed can be converted to cold air is going to be 38%. So 38% of the feed is converted to cold air. So now we're going to look at the second law. And what we're going to do is calculate the total entropy change, which would be delta S of our system plus delta S of the surroundings. If this is 0, no heat transfer to surroundings. This has to be greater than or equal to 0. To do this calculation, I can look at this system as if X moles enters and leaves, gets converted to cold air, and 1 minus X enters and gets converted to hot air. And I want the entropy change for each of those. So X moles times entropy change for what becomes cold air, and 1 minus X moles entropy change for what becomes hot air. So we'll make a couple assumptions. Ideal gas, these pressures, this is pretty reasonable. Constant heat capacity, these small temperature ranges, this is also reasonable. And we're going to assume this, we look up reference, this is going to be about 30 joules per mole Kelvin. So now what I want to write down this total entropy change as x times change for the cold air. Two reasons the entropy changes. One, because the pressure changes. R, so minus sign, the gas constant, the log of the final pressure over the initial pressure, plus the heat capacity, the log of the final temperature, the cold temperature over the initial, the inlet temperature. Keep in mind these are absolute temperatures. And then the exact same term for the hot air, except we have 1 minus x moles. So this term looks the same, except this is the hot temperature instead of the cold temperature. We're almost finished. We're going to substitute values in for this. We calculated x as 0.375, minus sign the gas constant in 8.314. This is units of joules per mole per Kelvin. And the final pressure is 1 bar. The initial pressure is 10 bar. Heat capacity 30. Again, joules per mole Kelvin. And the log, the cold temperature is 0 plus 273 to make it absolute. Inlet temperature 25 plus 273. And now we're going to have similar terms for the hot temperature stream. So here's the term now. This is for the hot temperature stream. Same calculation as cold temperature stream. Now, what I'm going to do is add together terms before I do the calculation. You can see we have the same terms here. This multiplied by 0.375. This multiplied by 1 minus 3.75. So when we add those together, it's 1 times minus 8.314, the log of 0.1. And then we can factor out the heat capacity and have a term. So now I've written the terms, the heat capacity and the two log terms, where I divided the temperature ratio. So now I just need to do the math to calculate these terms. Here are the calculations, and just point out a couple things. There's a minus sign here and a minus sign here. So overall, this term is positive. Namely, we decrease the pressure from 10 bar to 1 bar. The entropy increases. This term is negative because we've lowered the temperature. That decreases entropy. This is the term for the 40-degree stream. We have raised the temperature. That increases the entropy. You'll notice that this first term dominates, is much larger than these last two terms. So overall delta S then is equal to 19.1 joules per mole Kelvin. And the important thing is that delta S total is greater than 0. So the answer would be yes, this is possible. Satisfies the first law, satisfies the second law. The reason it's possible is because of this large pressure drop. That's a big increase in entropy. And this type of Hilsch tube exists. And you can, for example, check on the internet. You can actually purchase this. It's used to create cold streams in certain industrial applications where you have high pressure air.